We're at Northwestern University, and I'm a physicist. Okay, do you know what a physicist is? Yeah? What's a physicist? Anybody have an idea? What do you think I do?
Something to do with physics.
Good guess, yeah, that's right. So I work at one of these gigantic laboratories, like the ones you see in the newspapers that smash things together, really high energy. And then we do experiments to figure out things about nature, like the fundamental laws of nature and what are the fundamental constituents of nature. You know what I'm talking about? Sort of. Are you all very shy? What grades are you in? What grade are you in?
Turning to junior.
You're going to be junior?
Yeah.
Oh wow, you guys look so young to me.
Mine's
Must
at,
be that I'm really old.
I'm going to Northwestern University.
No kidding.
July 21st, we're August.
Oh, fantastic. Well, so what do you like to do? What do you like to study?
I was trying to study computer science at first, but I didn't reach the requirement, so I had to take AP statistics.
Oh, that's not bad.
Yeah.
You can make a lot of money in statistics, you know. How about you? How old are you?
15.
15? Do you know what you want to do?
Not yet.
Yeah. Not physics?
No.
No? How about you?
I'm going to be a junior.
Okay. And what do you want to do?
Chemical engineering.
Chemical engineering. That's a good choice. That has a lot of physics in it, actually. So have you all had a physics class already? No. So you don't know any physics at all? I could tell you whatever I wanted and you wouldn't know the difference. Now, don't worry, I will tell you the truth. Okay, so you all have these nice books, which actually I don't have. I only have a really old one. And have you finished reading it? Did you look at it at all? No. Well, here's the thing. In order to do well on this, I had to read up a little bit because this didn't exist when I was your age. Okay, so I had to take something else called the SAT. But it's the same idea. And the purpose of this test is not to see if you know all the facts of physics. That's not the idea. Okay. The point of this test is to see if you've got a brain. So raise your hand if you have a brain. Yeah, you think? So all you have to do is to use the brain in a good way, and you'll do fine on the ACT. All right, so what I want to do is to pick out a couple of example questions, maybe talk a little bit about in general. It's not my idea to try to teach you all of physics in an hour and a half, even 3 times an hour and a half. That's not possible. You know, I teach physics at the university and students study for 7 years all the time. And even then they don't know all of physics. So we can't have as our goal today to learn all of the physics that might be on the ACT. What we have to do is to figure out how to deal with the physics questions and other science questions that are on the ACT. You know what I mean? So do you know algebra? Yeah? Okay. So let's start with something really simple just to get warmed up. So I'm going to take a mass, a body, a block. You know what I mean? Just a big block of stone, something like that.
I'm sorry, you can use the black one instead of the
Yeah,
green
this
one?
is the black one?
Yeah, I'm sorry.
Oh, in here.
Yeah.
Yeah, the green one is,
Yeah.
yeah.
It's much better.
Yes, it certainly is. So just think of something that's about that big and weighs a little bit, okay? And it's sitting on the table, like this table here, and someone has brought in a spring. You know what a spring is? A spring is this curly thing that if you stretch it, it pulls back in, right? So if I attach a spring here, and attach it to the mass, I have what's called a harmonic oscillator. Okay, so have you ever heard of a harmonic oscillator before? No, okay. So you don't have to take a whole bunch of notes. You mainly just have to think about the strategy when I tell you. Okay? Now, I'm going to imagine pulling on this. Okay? So I'll pull with a force to the right, because I want to stretch the spring and see what happens. Well, we all know what's going to happen, right? If I let go, it's going to go boing, 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 like that. That we kind of know. We're trying to think about it the way a physicist would think about it. And so one of the things a physicist would draw is a graph. What's a graph? You know what a graph is, right?
Yeah.
Tell me, what is a graph?
The data thing.
It's a data thing. All right, what a great definition. Yeah, it's a data thing. So it's a data thing which has two lines. So my teaching style is to make jokes a little bit, but still try to pay attention, okay? All right, so this data thing I'm going to draw, this graph, is going to have on the horizontal axis something I'm going to call x. Okay, and x represents how far I pull it. Okay? And then this vertical axis here, the one that's going up, I'm going to draw the force. And when I say the force, you probably think of some movie or cartoon or something. But what this force means is what you feel when you pull. So you pull the spring out, and you can feel, because you have muscles in your fingers and your arm, you can feel that the spring wants to contract back to its normal position, right? So just imagine that in your mind. You pull the spring out, if you let it go, it's going to go flying back in. So you know it's pulling back in. And what we call when that pulls is a force. Okay? All right. So the question is, what's the force as I pull this out? All right? What's the force as I pull it out? Does it get bigger? Does it get smaller? Or does it stay the same? So what do you think? If I pull it out like that, would you say that the force is going to stay the same as when I have it there? No. That would be silly. Right? Do you think that if I pull it out, the force is going to get less? No, that actually makes no sense whatsoever. How could it be really big there and really little over here? That would be bizarre, right? So the only really answer that makes sense is that if I pull it out, the spring that is pulling back, the force of the spring increases, right? It gets larger. So the more I move to the right, the more the spring pulls back. Now if I go to this data thing, and I draw a line that represents that the force goes up when the displacement, when x, this distance here, goes up, what kind of line am I going to make?
Positive.
Positive. Hey, positive what? That's exactly right. Positive what? Positive line. It's going to go like this. So what we say is that the slope is positive. Okay, the slope means the slope is the change up divided by the change across. Okay, and so this line that I drew there is an example of an increase as a positive slope, just like you said, positive slope. All right, so it increases, and that means a positive slope. Okay, everybody got that? Okay, you're already a physicist. Sorry. Okay, well, one way to make sure you really understand something is to try to imagine what would be different than what we just talked about. So if I wanted to draw a line that showed the force decreasing, not increasing, but decreasing with x, what would that line look like? Let me give you a hint. If the slope is positive for an increase, what's the opposite of positive?
Negative.
Negative. So what does a line look like that has a negative slope, do you think? Goes down. Yeah, it's as simple as that. So I'm going to draw it just in dashes because this is the wrong answer, but the point is that would be one that decreases as x increases. Okay? Now the reason why I'm spending a lot of time on a graph like this is that a whole bunch of the questions you'll see on the ACT are all about graphs. Okay, so I'm using a simple example here of a spring to talk about graphs. All right, so let's do another example of a graph. Okay. All right. So it's kind of nice today, a bit warm, right? But sunny, we're in summer. So what I'm going to draw on the horizontal axis is time. Okay? And I'm going to say that this is the middle of the night, this morning, right? This is noon. Okay, so we're like here. And then over here we're going to say this is midnight. So that's late tonight when you're all sleeping. Okay? So this represents 24 hours. Now, what I want you to tell me is if I had a thermometer outside the window that registered the temperature of the air, what kind of curve would you expect to draw to represent how the temperature varies with the hour? What do you think? I know sometimes it's hard because you can have a whole bunch of rain like the other day. Did you have, any of you have trouble with the big flooding the other day? You know, my street was flooded, it was under this much of water. I had to get my winter boots out and go slosh, slosh, slosh just to get out of my house. It's terrible. But today has been kind of a typical summer day. So who wants to take a shot at this? Yes?
It would be like a hill.
It would be like a hill, great. Hill is an excellent answer. Be like a hill, right? In fact, I'm going to use that next time I teach this. It looks like a hill. So why is that the right answer, everybody? Why is she right? Yes?
Because in the morning, isn't it colder? So like it start like down, and
Yeah.
then during the daytime it's hotter. So like you
Yeah.
go up and then it gets colder down.
Exactly, right? So my kids, when they get up in the morning, they sometimes have to put a sweater on or something because they're skinny and they freeze in the morning. And then in the middle of the day, they all are in shorts and t-shirts and they're outside playing frisbee and stuff. And then at night, they have to put the blankets on, just because of the reason you said. Great. So notice that the temperature is increasing in the morning. And there it is again, that sort of positive slope. And then it decreases in the evening after the sun goes down, right? Now what about at 12 noon, the top of the hill? Is it increasing or is it decreasing or neither? Right here. There's a certain point at the top of the hill. What would you say? Is it increasing there? No, because it's not going up anymore. Is it decreasing? Not really, because it hasn't started to go down. So this is something what we call, that's the maximum. Okay, maximum is a word that just means the highest of. Okay, so I can ask you all to stand up. I can look at your heights, and I suspect that you will be the tallest one, because you look like the tallest one. See the tallest one? No? All right, stand up. Let's see who's the tallest. Sorry, we didn't make it. He is. It's pretty close, but yeah, you with the blue, with the green shirt, you're the tallest one. Okay, sit down. So in terms of the height, he has the maximum height. Okay, and I think one of you had the minimum height. Okay, you know what? I have the maximum age. Okay, and you guys are all much younger than that. Okay? So, when you see a graph, the first question is it going up or going down? Sometimes you get a graph like this which is doing both. It's going up and it's going down, and then you have to see, okay, where is it going up and where is it going down and why? All right, so when you take the ACT, you'll see bunches of graphs like this, and then they'll start asking you questions about what's going on. Okay? And the first thing you have to do is to find the line, think about it going up or going down, look at what this axis is, and look at what that axis is. Now notice in this example, we're clearly saying that it's the temperature that's going up and down. It's the temperature that depends on the time. It's not the other way around, right? If I drew a graph that was flipped, that had temperature here and time here, so this was night, this is day, and this was night, then I would have, again, the hill sort of sideways like that. But this wouldn't make any sense, because the time doesn't change as a function of the temperature. The temperature varies as a function of the time. You know what I mean when I say as a function of? It like depends on, you know what I mean? Okay. All right, so it's really important, if you don't know what the graph is about, to think about that this thing is what depends on that thing. Okay. So let's do another example from something called mechanics. So what I'm going to do, again, is a function of time. I'm going to plot the position of something, all right? So we're going to call this height, okay? And the thing that I'm going to plot the height of is this pen when I drop it. Watch. Watch which way it goes. It went down. Yeah, of course, where else is it going to go? So if I want to make a plot now of the height, you know, with respect to the floor, as a function of time, what's it going to look like? Yes?
Like straight down.
Straight down. Almost.
Kind of.
Certainly it goes down, so you definitely are on the right track.
Like a little bit, like slanted to the right.
Slanted to the right, yeah.
like over-
Yeah, sort of like this, right?
Yeah.
But the important thing is that it's not just a straight line. It turns out it will be a curvy line, okay? It will look like this. Okay? So it's unfortunately it happens so fast we can't really tell. But when you drop something, it starts out slow and then it goes faster and faster and faster until, of course, it hits the ground. Anybody here ever go skiing? Yeah? So it's the same thing. When you start out on the slope, you know, you do your initial nudge and you start doing, and then when you get to the steep slope, then you really accelerate and go super fast, right? The same thing here. So we understand that the height is varying as a function of the time. Okay? We also see that the change in the height is slow at first and then it's fast at the end. Okay? This fact that it has a curvy part to it, that it's not just a straight line, is due to something called acceleration. Okay? It's due to acceleration. And if I wanted to write an equation, an algebraic equation that represents this line, I could write something like the height is an initial height, h sub 0, minus, turns out is 1/2 g t squared. Okay, now does that mean anything to you guys? Have you done that kind of math before? No? Anybody? It's okay if the answer is no. You're students, you're not supposed to already know everything, right? Okay. So I need an answer because I can assume that you know, and then you won't understand anything I'm saying, and we'll all get bored, okay? Or you can say, oh, no, I don't quite know what that means, Professor, and then I'll try to explain a little bit and see what you do know.
I don't quite know.
You don't quite know. Thank you. Thank you. All right, so have you ever graphed things like y equals mx plus b. Does that ring a bell? Yes, you all know that? That's the equation for a straight line, right? Okay. This is a slope, and that's the intercept. Have you ever seen equations that look like this? Y squared, or ay squared, plus by plus c equals 0? Yes? So what kind of curve is that? Huh? It's a hill.
Quadratic.
It's a quadratic equation, great. It's a hill. The sort of more official name for that is a parabola. Okay? It's just a name. This is an example. If I continued the curve to the other side, it would look like that. And now you all say, ah, yeah, of course, if you drew it like that, I would know right away that that was a hill or a parabola. Okay? So this equation is quadratic in time. Okay? So this one's quadratic in y, but this is not the right equation for what we're looking here. It should be quadratic in t. It should depend on t squared, t to the 2. Okay? Now, the question is why? Why not something simpler, like h equals h0 minus v times t? Why not that? Okay? This would be a linear equation, depends on 1 power of t, and the graph for that would simply be this. Okay, so this is linear, and this is quadratic. So, am I picking this just because I want to make the problem hard and frustrate everybody?
No.
So why did I write it this way? There's actually a really good reason why I wrote this and not that. This is easier. Maybe I should just be nice and make all the questions easy. But I didn't. I picked this. Why? Why do scientists believe that if something falls as a function of time, it starts out slow and the end is going really fast? Why do you think someone like me believes that? I believe it all the time, every day, forever. I will always believe that that's the truth. Why?
Because if it stays in the air, the longer it stays in the air, the more gravity will.
Yeah, you're on the right track. Actually, you're on the right track. It has something to do with gravity, but I'm actually asking a different question about science. Okay, science. If we want to understand something in science, say physics is an example of science, how do we understand something? What do we do? Do we look it up? Do we go to the magician and ask the magician, try to do something to make this happen? How do we know that something's true in science? Yes? We do experiments, right? And we observe, and eventually we write down mathematical formulas that tell us the results of those experiments. Okay? So the reason why I wrote this down is because experiments tell us that that's the right answer. And if it's complicated, too bad. That's the way nature is. Okay? So an important basic idea of science is that you have to conduct experiments. They have to be valid experiments, which means you have to know how to do them. You have to observe and figure out what the experiments are telling you, and then eventually you have to come up with rules and results that tell you the results of the experiment. Okay? So there was this guy named Galileo, and he did a bunch of experiments that helped him figure out that this was the right answer. Okay? All right, so even though this equation would be easier to solve, this is the right one. All right, so we'll erase the wrong one and keep the right one on the board. Okay. So now you mentioned gravity. Gravity is definitely the main character in the story here. Okay? So if I hold this pen up here, if I drop it, it will fall, right? Why does it fall down instead of falling up or out the door? How come, like in the movies, with, what's her name? I Dream of Jeannie. Have you ever seen I Dream of Jeannie? No? Okay, that's an old show I used to watch when I was little. And it had a person who could do magic. And so she would make things float out the door and all that. Of course, that's not real, right? But it made a quick movie. In reality, if I let this go, it falls down and hits the floor. Why? Why does it go down instead of to go some other direction? Why do you think? You mentioned gravity. That's actually the right answer, but can you say more about that?
It's because the Earth is such a big, like, object compared to, like, all the other stuff that the Earth's gravity outweighs the gravity of other objects.
Wow. That's a sophisticated and very correct answer. Good for you. Okay? So I'll repeat. Okay? So gravity is the force. Remember we were talking about forces in the beginning? Gravity is the force that pulls us towards itself. Okay? So when this falls, it's not falling down, it's falling towards the center of the Earth, which happens to be down there someplace. If you go to Australia where the kangaroos are, they're kind of upside down compared to us, right? They're in the southern hemisphere. When they drop their pen, it doesn't like go down, it goes also to the center of the Earth, right? So we're over here in Chicago. If we drop a pen, it goes towards the center of the Earth here. If there's someone in Australia and they drop a pen, it also goes to the center of the Earth. Someone over here in France would go to the center of the Earth. Okay? So gravity, just like you said, is the force that the Earth creates that pulls things towards the center of the Earth. And because there's a floor here, we don't go towards the center of the Earth. Okay? So gravity is what's responsible for this change. If we didn't have that, then we would just have that the pen floats in space at the initial height, and that's clearly not true. Gravity accelerates anything that we drop so that it hits the ground. Okay? Could be a basketball, could be a golf ball. And it's good for us because otherwise we'd all be floating around and wouldn't be able to go anywhere. Okay? So let me draw another graph. I'll draw one more graph and then we'll talk about experiments. So the law of gravity, there are two of them, but Newton's law of gravity can be written this way. Okay, so let me try to explain what that is. Here's the Earth, okay? And out here is the moon. And there's a certain distance, d, from the Earth to the moon. Okay? Now, if the moon was free to move any way it wanted to, it wouldn't hang around the Earth. The reason why the moon stays close to the Earth and we see it every night, at least when it's not cloudy, is because of the force of gravity. So gravity causes the moon to be attracted to the Earth. And it causes the Earth to be attracted to the moon. Now, there are many variables here. This m1 would be the mass of the Earth. m2 would be the mass of the moon. Okay? And d, as I wrote, is the distance between them. So I want to make another graph now of that force as a function of d. So we were doing a couple of graphs as a function of time. Yes?
Can you drink water?
Can you do what?
Get a drink of water.
Yeah, please.
Okay.
So I was drawing graphs as a function of time before, right? We talked about